Right, so good morning. The YouTube stream has already started, so we are ready to go. Another 2 minutes or a half or so. All right, so I posted a question in the questions channel on the Discord server. The link is already posted. It's not pinned, but it is posted in today's text channel. So I would definitely look at that as an exercise of how to figure out the probability of something. Danny asked a good question about that question itself, because I did not specifically spell out that it is without replacement. So that really helps to narrow things down, significantly, because it is without replacement. Now that we know that it is without replacement. So we have a few things to finish up today. I am going to talk about Pascal's identity and also the binomial theorem. And we'll talk about the proof itself, all the algebra stuff. And then I will kind of, that should end the topic of discrete probability. And then we're going to move on to something new. And we have a few choices. I think I'm going to focus on graph first, because that is an important topic. Not that the other topics are not as important, but the graph topic is, I would say, particularly important. So that's what we're going to do today in 1 more minute. So we got 1 more minute before the class starts. And I'm just taking a look at the live stream, making sure that's healthy. Yep, we got 1 person watching from that side. I can now close my YouTube monitor, so with this way it doesn't use up any additional resources. The computer I'm using right now, I bought it more than 3 years ago, and it's really just a laptop computer. I wouldn't say it's a bottom of the line, laptop computer, but it's not really, specifically powerful either. It's just a little Lenovo desktop computer, and it's still, fast enough for what I do. So I'm, pretty happy about that. I don't have to buy a new computer, not anytime soon. And let me mute all my stuff here. Okay, that should be muted now. All right, it is time to get started. So I am going to, kind of go back to where we left off last time. So what I am going to do today is really just kind of go through the proof itself. Because this is algebra. As I said, it's just the only part that is tricky about it has to do with the telescoping effect of factorial, especially for Pascal's identity. All right, so I'm going to get started here. If you have any questions, go ahead and post it in the text channel, or you can use the voice channel to ask questions as well. As usual, nothing, there's nothing, nothing has changed. All right, so the first thing is, last time when we talked about this, it was in conjunction with an actual display of Pascal's triangle. So what we're going to do today is simply to go through the proof itself. And Pascal's identity is actually a proof of why Pascal's triangle works. So that's kind of the context of Pascal's identity. So what we want to do is to prove that n choose k plus n choose k minus 1 is the same as n plus 1 choose k. So that's what we want to prove. So the rest of these steps here, they are basically algebra. On the first line, between the left-hand side and the right-hand side, that's just the definition of choosing. In other words, the way we compute the number of combination of n choose k is n factorial divided by k factorial times n minus k, the whole thing factorial. That was discussed in the counting module. So not in this particular module, but in the previous module, when we talked about counting. So n choose k minus 1 is about the same. It's just a little bit clumsier because instead of k, now we have k minus 1. So that's what line 1 is about. It is just using the definition of n choose k, or the way we compute the number of combination, and just expand from the kind of clean, easy format to the format that uses factorial. Between line 1 and line 2, the only change is right here. So if you look at the denominator of the right-hand side of the addition, the n minus the whole thing, k minus 1 factorial, is rewritten a little bit as n minus k the whole thing plus 1. So that's just basic algebra here. By regrouping the parentheses a little bit. So are there any questions about how we went from line 1 to line 2? All right, I'm not seeing any questions. Now let's move on from line 2 to line 3. So from line 2 to line 3, the change is somehow the numerator of the right-hand side of the addition now has a k. But you can see that there's also a change down here. So instead of k minus 1 factorial, this is now k factorial. So this is because in k factorial is k times k minus 1 factorial. And so in other words, I introduce a k on the numerator, but I also introduce a k in the denominator, because k divided by k is 1, so it doesn't really change the value, but it does change the way we express the denominator, because it used to be just k minus 1 factorial, and now I can write it out as just k factorial. But in order to compensate for the extra k in the product in the denominator, I also have to multiply n factorial by k in the numerator. So this way, everything kind of balances out, and this equality is going to hold. So are there any questions going from line 2 to line 3? All right, line 3 to line 4. So line 3 to line 4 is, once again, doing a trick kind of like that. So I take the last term of n minus k the whole thing plus 1 factorial. The very last term of this factorial in this product is n minus k the whole thing plus 1. So I took that out and decide to move it up to the numerator part. So that way n minus k plus 1 factorial becomes just n minus k the whole thing factorial, because the last term, the very last term of the product, is now moved to the numerator of the right-hand side of the addition. And then from line 4 to line 5, I decide to do the same thing on the left-hand side of the addition. So, instead of using, oh, I take it back, never mind. This is actually easier. It's easier because, n factorial becomes n factorial times basically 1, because I introduce n minus k the whole thing plus 1 as the numerator, as well as n minus k the whole thing plus 1 as the denominator. So basically, we have the same value divided by itself, and it cancels out. So it doesn't really change anything. It just makes it look kind of clumsy. So by doing this, I have accomplished one thing. I have unified the denominator, right? Like here, I have also unified the denominator here as well. So by doing that, I can now say, okay, since the denominators, okay, there are two, are the same, I can now unite the numerator. So the numerator, which is n factorial times n minus k plus 1, and n factorial times k, that becomes just one single addition. But the the denominator, on the other hand, they are unified. So by rewriting the n minus k plus 1 as a part of the outer denominator, just move it down a little bit, then we end up with k factorial times n minus k factorial times n minus k plus 1 factorial. And then on the other side, we also have the numerator. I did some work with the numerator as well. So n factorial times n plus 1 is n plus 1 the entire thing factorial. So that gets simplified out a little bit. And this is using Oh, this is using distribution. So n factorial times k is also singled out, and it is a subtraction because in the original expression we have n minus 1 minus k. So the n plus 1 itself is merged with n factorial to become n plus 1 factorial. The minus k is just multiplied to n factorial. That's nothing I can do to kind of merge it with anything. And then we have the plus n factorial k down here, which is inherited from the previous line. But this way, I can now cancel out the n factorial k, the subtraction of that term, and then the addition of that term. That kind of cancels out. So now we end up with n plus 1 factorial as the numerator. And then the denominator, I just kind of fold the n minus k plus 1 factorial into n minus k, excuse me, I take it back. I fold the term n minus k plus 1 into the factorial of n minus k. So, it becomes n minus k plus 1, the whole thing, factorial. So once we have it in this format, we rewrite it one more time by grouping n plus 1 as one thing, and then the subtraction by k as the other thing. So once we have this format, then we recognize it as, oh, so that means it's just n plus 1 the whole thing. Excuse me, n plus 1 choose k, because this is how n plus 1 choose k would have expanded based on the definition of how we compute the number of combinations. Whew, okay, so are there any questions about the algebra of this derivation? Alright, so looks like there are no questions about the algebra of this derivation. Cool. Alright, so next we're going to prove the binomial theorem, and this is the binomial theorem right here. It looks really kind of simple, because all it is trying to say in overall is to say p plus q to the power of n is the summation of I going from 0 to n, and then each term that we are adding in this gigantic summation is n choose I times p to the power of I times q to the power of I n minus 1. And this is the one that I explained the other day, which is the technique of proof by induction. So in proof by induction, last time we also talked about how we have a base case. So the base case typically is to choose one of the values over in the range over which the theorem holds. So in this case, the theorem, which is p plus q to the power of k of n, is the sigma of this entire thing here. That equality should hold as long as we have n being a non-negative integer, or otherwise known as a natural number. So that's the entire range of what value of n this particular theorem should apply to. In proof by induction, what we do is we pick a specific member of that set. Okay, so in this case, you typically pick one on one extreme or the other extreme when there are extremes. So when we talk about natural numbers, one end does have a very specific extreme, which is 0 itself. So we chose to use n equals to 0, and we established that when n equals to 0, the theorem is true. Okay, now that's not really super helpful in terms of proving the entire theorem, but it is a necessary first step. Okay, so the first step is to pick a value and prove that. Now, some people may be asking, what if a theorem is supposed to be true over all integers? In other words, there's no natural extreme constant that we can use. Well, in that case, you have to break it up into two theorems. One theorem says from 0 to all non-negative integers, and then the other one will start with -1 and then go to the negative side for all negative integers. So you basically have to break it up into two parts, and then each part has its own base case. All right, or you can share one base case, which is just 0 itself, but then you need two induction steps. One to go forward, to given k for n equals to k, the theorem is true. You want to prove the case when n equals to k plus 1, and then you need another induction to go in the opposite direction, which is given that when the theorem is true when n equals to k, then you have to prove the theorem is also true when n equals to k minus 1. So that's just one extra branch when we are trying to do the induction step. All right, so the actual proof is a little messy. I'm not sure last time whether we talked about, I don't think we talked about this proof last time, so I'm just going to go through this proof this time and explain the algebra of this particular proof. I really hope that most of you had a chance to kind of look through this over the weekend. Not because I'm going to ask you to prove something like this in the final exam, but to kind of confirm that you know how to do this, or at least you understand this particular proof. Any questions? All right, so I am going to check in Discord to make sure that I'm not just talking to thin air. Okay, I am not. Very good. Because I didn't check. I did not check how many people were on Discord. It's entirely possible that I just signed into the voice channel of CISP440 and keep yakking, and nobody was actually listening to me. That's entirely possible. I think I have done that in the past. So yeah. So in this case, we have given n equals to k is assumed. The theorem applies when n equals to k. Given that assumption, we use that assumption to prove that the theorem is also true when n equals to k plus 1. So that's, I would just kind of clarify what Elijah is quoting. Yes, so so the theorem being true when n equals to k is assumed. That is a part of the induction step of proof by induction, is you have to make an assumption that the theorem is true given n equals to k, and we don't really spell out what k is. Okay, so that's the trick. That's the part that gets most people is, but what is the value of k? For some k, for some value of k, that is what we say about the assumption. But the key here is from that assumption, the next thing you want to prove is the case when n equals to k plus 1. So that has to be consecutive. It has to be right next to the assumption itself. So that part is really kind of important. All right. All right, cool. No problem. So now we take a look at the actual proof. So p plus q to the power of k plus 1 is boiling down to p plus q times p plus q to the power of k. So that's just taking one of the terms of the power to stand on its own, and then the rest kind of is bunched together. So by applying the assumption, we go from line 1 to line 2. That's the application of the assumption, because by assumption we assumed that p plus q to the power of k translates to this sigma here. And then from here to here, it is just taking a term from outside of a sigma notation into the terms inside of a sigma notation. Typically, we want to do something, we want to simplify in the opposite direction, but in this case, this turns out to be helpful. And then from here to here, we basically just use distribution. So by using distribution, one side has an extra p term. This p here is associated with all of the subterms of the sigma on the left-hand side, and then the sigma on the right-hand side takes on q as an extra term. So that's why when you look at the powers of the p and q, the one on the left-hand side has an extra plus 1 when it comes to the power of p, and then the one to the right-hand side, q itself has an extra plus 1 when we look at the power of q. And then from here to here, I break up the first term. So let me just double check and make sure. Let's see. Oh no, I take it back. From this line to this line here. Let me see what I did. Sometimes I forget what I did. Oh, right. Okay, so from here to here, I separated one extra term over here and then one extra term over here. This one accounts for p to the power of 0, q to the power of k plus 1. This one accounts for the opposite, which is p to the power of k plus 1, q to the power of 0. So, and that accounts for this term here. You can see how this used to be from 0 to k, it is now from 1 to k. So when I equals to 0, that term is brought out to here. So let me just make it clear again, okay? This term here became this term, but the first term is out of the sigma notation, and it is standing on its own as in this form. And someone may say, but that's not the same, Tack, because, from here, okay, when you look at this particular term here, when I equals to 0, then we have k choose 0, p to the power of 0, q to the power of k plus 1. This one has most of everything being the same, even the 0, I being 0, they're the same. But this is k plus 1 choose 0. This is k choose 0, so they cannot be the same. So what do you think? Why do you think I made it? How can I make it like this? Okay, so that's the question. Now this is kind of important because this is what I would call the telescoping effect of the sigma notation. But at the same time, I'm also exploiting one special case for computing the number of combinations. So what happens when you choose 0 out of n? What is the answer to that question? It is always 1, exactly. So k choose 0 is 1, k plus 1 choose 0 is also 1. So when I took the first term out of this sigma notation out to be its own term, I could have written it just as p to the power of 0, which is also 1, and then q times k plus 1, q to the power of k plus 1. I could have just written it that way. But I'm going to choose to write the 1 as k plus 1 choose 0. There's nothing wrong with it. I mean, it just looks kind of odd. So I did the same thing from using, if you look at this sigma notation here, the last one of this sigma notation, which is when I equals to k. So when that happens, we have p to the power of k plus 1, q to the power of k, q to the power of 0. So that's basically this term over here is pulled out as the last term of this sigma here. And that's why when we look at this sigma notation, you're moving to here, the end index or the end limit is no longer k, it became k minus 1. So the extra term that got pulled out is supposed to be k choose k times p to the power of k plus 1 times q to the power of 0. But that's okay because k choose k and k plus 1 choose k plus 1, they are both just 1. Okay, it's basically the same trick that I did with the other one. So I just decided to write it out as k plus 1. Now, if anyone is asking, so how can you determine what to do for this kind of algebraic derivation? In my head, the compass, is basically saying, okay, we need the k plus 1 term, okay, when it was just k. That's the overall objective. So that kind of told me, kind of in a weird way that I needed to do something like this. Pull out a term that used to have k in it, and then change it to k plus 1. So that's kind of what I was doing. So I'm not sure whether this is helping you or not in terms of the next time you need to solve something like this in one of your other classes. But that's the trick that I was using. All right, so from here to here, okay, so from here to here, the focus is to unify the range of the index. So from here, in before, this I is going from 0 to k minus 1, and then this I is going from 1 to k, so they are different. And what I did is to change the way I express the term inside the sigma notation. So this way I can change the index to go from 1 to k as well when it was going from 0 to k minus 1. Okay. All right. Okay, so are we doing okay so far with how we went from this line to this line over here? All right. Cool. All right. Cool. So this is a very kind of useful trick, when you're dealing with, sigma notation or the pi notation, anything that has a telescoping um, effect to it, is try to unify the range of indexes first before you try to combine them into one. So now that we have both sigmas, having the I or the index going from 1 to k, now we can combine these two into one single sigma notation. So basically, we oh, by the way, the other thing we can also that I also did was to change the way P and Q get their power. So they end up being the same. Okay, this sigma notation end up being having the same terms as this sigma here. However, each term has changed so that by this is p to the power of I instead of p to the power of I plus 1, and then this is k minus 1 plus 1. And let's see, what did I do with the other one? Nope, there was no change to the other one. But this is unifying, not only are we unifying the indexes going from 1 to k, but we are also unifying these terms. P to the power of I times q to the power of k minus I plus 1, they are now the same between the two sigmas. So that makes it very easy, because now we can just take the coefficients and say, okay, k choose I minus 1 is one of the coefficients, and then we can use factoring to factor out p to the power of I, q to the power of k plus 1 minus I. So that becomes the factor that we factor out, and then the part that are not the same become its own addition. So that would be k choose I minus 1, and then k choose I. And this is where Pascal's identity comes in handy, because now we apply Pascal's identity and say, oh, but this is the same thing as k plus 1 choose I. Okay, so this from here to here, that is the application of Pascal's identity. And then from here to here, we're simply saying, oh, so this looks like we can kind of add to the sigma term here just by changing the start index to 0, because this thing here, okay, looks exactly the same thing as this here, while I equals to 0. So that's how we can extend the range of the index to 0. And then this thing over here looks also like a term like this part here, except it is for when I equals to k plus 1. So we can also extend the and range of the index from k to k plus 1. So we end up with this particular format, which is what we want, because now this is basically saying the theorem is also true for the case when n equals to k plus 1. So we have now proven the induction step. So when we have both the base step or the basis and the induction step both proven, then proof by induction is done. All right, so Danny has a question going back from line 4 to line 5. You got the first term on line 5 from the second term, from the third term in line 4. Actually, let me count. 1, 2, 3, 4. So the extra term here is coming from this term. Let me double check. The last term here, okay, so the last term of this is this term here. The first term of this is this term over here. So it's crisscrossing a little bit. The last term of the left-hand side is the last term is here. The first term of the right-hand side is here. There you go. Yep. Okay. Not a problem. All right. So that's it. I mean, this is the proof of the binomial theorem, which is very handy. Okay. So the binomial theorem is very handy when we need to compute probabilities. So this is when we want to actually apply this and to figure out some actual probabilities. So let's go ahead and take a look at some problems and see if we can apply this. See if we can apply the binomial theorem. Alright, so I'm going to use mousepad to describe the problem, and then we'll also kind of talk about the solution. No need to restore from before. Alright, so the usual, very good, the very common example of using binomial distribution is flipping coins. Okay, so if you have a con artist, okay, having a loaded coin, so that the coin lands on one side more frequently than the other side. So we want to kind of figure out, how is it going to affect the probabilities, right? So if you so let's describe the problem first. Okay, so we'll say let p equals to the probability of a coin landing on head. Okay, and as a result, we're gonna use Q first. Okay, and then later on we'll talk about why what is the other way to write Q. Okay, of a coin. Of the same coin, I should say, of said coin. Okay, there we go. Landing on tail. All right. So obviously, most people look at this and go like, tag p plus q equals to 1, right? Yep, that is true. Okay, not a problem here. So what we want to do is to say, let's just say compute the probability that out of 5 coin tosses, we end up with 3 heads and 2 tails. There we go. Alright, so are we understanding what kind of problem we are trying to solve here? So we have a coin that is potentially loaded, and I'm using a variable to describe the probability of the coin landing on the head, and then basically 1 minus that as the probability of the coin landing on tail. And my only interest here is to say, okay, out of 5 coin tosses, what is the probability of landing on 3 heads and 2 tails? And the ordering is not important. Yeah, yep, so sort of similar. But I want to show you how we solve this, right? So, so the equation, okay, if you want to look at this from the perspective of an algebra problem, is we have p plus q, okay, because p is the probability of landing on the head, q is the probability of landing on the tail, and we are basically looking at something like this, okay, p plus q to the power of 5, okay, and so now you look at this and go like, okay, so this is where we can apply the binomial theorem, right? Because the binomial theorem says, yeah, we know the coefficients of all of this stuff here. Let me take it back. 5 choose 0 is a 1. So, p to the power of 5, there's only one of those. And then the next one is 5 choose 1. So that means there are 5 of p to the power of 4 times q. The next one is 5 choose 2, which is 10. So we have 10 of p to the power of 3 q to the power of 2. And now obviously I can just stop here because we already have the term that we are looking for. But I'm just going to add up everything, just so that we reapply the binomial theorem, so we can actually see the end result of applying the binomial theorem on a problem like this. So the next one is going to be 5 choose 3, which is also 10, and this time we have p to the power of 2, q to the power of 3, and then we have 5 choose 4, which is 5, and that would describe p times q to the power of 4. And last of all, we have 5 choose 5. That's going to be just 1, and that is the coefficient of q to the power of 5. Alright, so I'm just going to pause here and make sure that everybody can see that this is just a concrete example of applying the binomial theorem. Are we okay so far with that? Alright, very good. And some people will look at this and go like, but Tag, this entire exercise is pointless because we know that p plus q is 1, right? And 1 to the power of 5 is just going to be 1. So why bother with all of these extra terms here? What is the whole point of doing this when we already know that the summation is just going to be 1, okay? Because 1 to the power of whatever is always 1. So what is the whole point of this exercise? Well, if you read the question, we are interested in one of them, right? Now that only has to do with how we formulate the question, because I could have formulated the question of we ending up with more heads than there are tails. So in that case, we will also have to include 4 heads and 1 tail, and also 5 heads and 0 tails. Okay, but in this specific case, I'm only interested in 3 heads and 2 tails. So that means the only term that I'm interested in is this one here. This is the only one that I'm interested in, and that certainly is not going to be 1, right? Because what this value is really depends on what p and q are. Okay, now q is not very interesting because q is really just 1 minus p, so everything boils down to what is the value of p. Because we are raising p to the power of that is 1 more than q is, so that means if p is larger, then this value is going to be leaning on the higher value side compared to a balanced or non-loaded coin. On the other hand, if p is smaller than 0.5, then this value, the value that has all the carrots pointing to it, is going to be smaller than what you would expect from a coin that is not loaded. So are we doing okay so far with this specific example of how we apply the binomial theorem to solve for a particular probability? All right, very good, excellent. So I'm just going to put this, I'll just put it here because it's important to understand that q is not an independent variable. It is just 1 minus p, and that's why given a specific p value, we can now solve for this value here. All right, so did you take on computer science as a major just so that you can figure out the probability of coin toss cases and try to determine whether a coin is loaded or not? Is that kind of your objective of taking on computer science as a major? All right, well, there's nothing wrong with that too. Not at first. All right, so the question is, how does this map to something that's actually useful in computer science? Because as long as I don't gamble, why would I need to know, the chances of, coin flips and whatnot? Well, as it turns out, there are a lot of things in computer science that are also binary in nature. Either it is or it is not, okay? One thing that is like that is transmission of a bit, okay? So when you're transmitting a bit, okay, it doesn't matter whether it's over fiber optics or over Wi-Fi or over Bluetooth or whatnot, there's a chance that it may not be received correctly. Okay, so the bit that is being transmitted from the transmitter's perspective may not match what the receiver is actually receiving. So there's always a probability that it is not going to work. Now, the actual physics of why you may not be receiving a bit the way it is intended, there are many things. I mean, if you're talking about Wi-Fi, especially the old 2.4 gigahertz Wi-Fi, if your computer is between if there's a microwave oven between your computer and the Wi-Fi base station, someone just has to nuke something, an instant noodle or something, and that can interfere with your reception right there, okay? Because microwave is operating at about the same frequency, and a microwave has a very, very powerful transmitter that we call a magnetron. And you heard that right, it is magnetron, not megatron. Okay, anyhow, so there's a chance that you may not be receiving a bit correctly. So why do you want to know the probability of not receiving a bit correctly? And this has nothing to do with you trying to become a computer scientist or becoming a software engineer. This has to do with you being a gamer, or this has to do with you watching a movie. Because if that packet, especially with UDP, which is not connection based, so with UDP, there's no chance, or at least it's not built into the protocol, that the recipient will tell the receiver, whether the bits were received correctly or not. There's no receipt being done. Okay, there's a whole bunch of stuff missing in UDP that you actually have TCP, but we are not going to talk about networking topology or connectionless versus connection-based communication. But the bottom line is, if you know the probability of a packet, like let's say 1024 bits, okay, not being received correctly, that may be helpful to determine whether you can get the bandwidth that you need to watch a movie, or whether you can get the short lag time that you need in order to play a game successfully. So now suddenly people are interested, right? Now suddenly half the class is now awakened and go like, okay, so I guess I do need to know how this works. So in those cases, okay, you just look at very extreme numbers, okay, because the probability of a bit, not being received correctly, is pretty small. But nonetheless, we are still looking at a binomial distribution. So let's just say that one packet has 1,024 bits, okay. And let's just say that the packet itself has a self-correcting code, so you can actually self-correct up to, let's say, 2 bits that are transmitted incorrectly. So 3 bits or more, you're screwed. Okay, that packet is useless. But if you only have 2 bits, being transmitted incorrectly, the packet, or there's an algorithm to self-correct and go like, yeah, we can figure out that this bit is wrong, that bit is wrong. Let's flip those 2, and now we're good again. So now the question is, what is the probability that a packet needs to be retransmitted because you have exceeded that limit? Up to 3 or more bits are erroneous. That's binomial distribution right there. All right. So does everybody kind of see why that is binomial distribution? You just basically end up with a very, very, very loaded coin that's almost all the time, like 99.999%, landing on one side. And you're going to flip the coin 1,024 times. And your interest is, what is the probability that we end up on one side, like twice, once, or 0 times? Because those are the cases where it is okay. And in all of the other cases is you have to retransmit the entire packet. So that's one potential application of the binomial distribution. Are we doing okay so far with this? Cool. All right. So I'm going to summarize here. Okay, this is actually going to be useful, for those of you. Well, I shouldn't really say that, should I? For everyone, because we are all going to try to answer the question in the questions channel. The link to that question is already in today's text channel at the very top. Okay, so I'm going to rephrase what I just said. Okay, since we are all trying to solve that problem, it becomes important to understand how we classify a problem. Okay. So the first question, so we can answer those, we can determine the nature of the problem by asking and answering some questions. Okay, so the first question, and I'll try to write this in a specific way. So the first question is going to be, all right, so how do we go from spelling out the probability to putting it in the equation? All right. Okay, so I just missed a bunch of stuff happening in the text channel. Let me go back and reread those questions. So I'm going to start with Danny's question at 12:35. Wait, I'm sorry, going back again for a second. So the answer to that 5-coin toss question is just 10 times p to the power of 3 q times q to the power of 2. Yes, that would be the answer to the question of the probability that out of 5 coin tosses we end up with exactly 3 heads and 2 tails. But ordering is not important. Remember, we are only looking at combinations here. So that should answer Danny's question. Seems kind of similar to binomial and power series in calculus 2. Yes, it is the same thing. I mean, look at this. Look at this. This is just a, binomial thing. I mean, we are just, I'm glad you guys are seeing the similarity or the connection between those two concepts. Very good. How do we go from spelling out the probability to putting it into the equation? It's more like the other way around. The equation is what is giving you the probability, because this would be the probability of landing on 5 heads. This would be the probability of 4 heads and 1 tail. This is the one that we are looking for because our problem is 3 heads and 2 tails. This is the probability of 2 heads and 3 tails, 1 head and 4 tails, and this would be the answer to what is the probability of landing on all 4 tails given 5 coin tosses. So I hope that answers Elijah's question. It is actually the opposite. This basically expanded sigma notation is giving us the probabilities of each specific case. And which one do you want to add up to be the probability that you are interested in? Kind of depends on what your question is, right? So if your question is what is the probability of we ending up ending up with more heads than there are tails, then you want to add up these 3 numbers, because all of these are representing 5 heads and 0 tails, 4 heads and 1 tail, and 3 heads and 2 tails. So these are the ones where we have more heads than there are tails. So which part of these terms you want to add up kind of depends on what you're trying to figure out. All right, so Eric is asking, all right, is the probability of each case equal to the coefficient of the term divided by the sum of all the coefficients? Okay, let me parse that sentence again. Is the probability of each case, which is one of these terms, which is also one of the terms in the sigma notation, equal to the coefficient of the term divided by the sum of all the coefficients? The answer is yes and no, or in the most typical way that, okay, I hate to bring up Myers-Briggs type indicator thing. In the most typical way that an INTP would answer a question, it depends. It depends. So if P and Q are the same, if they're both 0.5, then Eric's observation is true. Okay. On the other hand, since P is not necessarily 0.5 because it is just it only has to be a number from 0 to 1 inclusively, right? So that means it's not necessarily the case. Okay, so that's why I answered that question with a it depends, okay? Because if P and Q are the same, then what Eric said is going to be true, because it doesn't matter whether it is just P to the power of 5 or P to the power of 3 times Q to the power of 2. If P and Q are the same, then for every single term, ignoring the coefficient, the product of the power of 5 and the product and the product of Q, excuse me, the power of Q, those would always multiply to, guess what, 0.5 to the power of 5, right? So the only difference will be just be the coefficient, but that's very specific. Okay, that is only specific to the case when P and Q are the same. Now, since the coin can be loaded, that means P and Q are not necessarily the same, and when P and Q are not the same, then what Eric wrote in the text channel is not going to be true anymore. All right, so let me just make sure that I answer that question okay. All right, cool. All right, so getting back to trying to figure out what kind of a problem you're dealing with. So there are many ways to start. I mean, there's no quote unquote best way to start. So I'm just going to throw out these questions in a kind of more or less random manner. The first thing is, do you have with or without replacement? Okay, this is a very important one. So we're going to say, okay, there are only two subcases here. So with replacement is going to have its own category, and then without replacement is going to have its own category. So in the case of without replacement, okay, then the next question you want to ask is ordering important? And obviously that also only has two possible answers, right? So if you say ordering is important, then we conclude that we are dealing with permutations, and each outcome is a tuple, because in the case of a tuple, ordering is important. Okay, a tuple is an array basically. And on the other hand, if ordering is not important, then you're dealing with combinations, and in that case, each outcome is a set. All right. And obviously, in terms of the calculations involved, in this case, we are going to use permutation. Okay, so if you're looking in a spreadsheet, it's called permut. Needs to be involved somewhere. Okay, I cannot tell you exactly how we apply it, but because that depends on the problem. But we know that if you want to count the number of permutations, then the function called permutations is going to be helpful. And when you want to count the number of combinations, then the function called combin, in the case of a spreadsheet, is going to come in handy. So next is to go back to here. What if we're dealing with a case where there is a replacement? So coin tosses is with replacement, because if a coin lands on the head the first time, it can still land on the head the second time, and the third time, and the fourth time, and the fifth time. So that is with replacement. So the next question you want to ask in this case is the cardinality of trial outcome, does it equal to 2? Because if it does equal to 2, we have a special case. It is a binomial distribution. Binomial distribution. And if it is not the case, then we have a different thing. So if it is not, okay, so let me just kind of rewrite it a little bit. The cardinality of trial outcome, which basically means for each step, for each trial of the experiment, how many possibilities can be the outcome for each trial of an experiment. If it is exactly 2, like a coin toss, then we have a binomial distribution. If it is not, okay, so we'll say the cardinality of the trial outcome does not equal to 2, which typically means it's 3 or more, because it's kind of meaningless if it is just 1. So typically it is 3, 4, and so on. So in that case, we're dealing with just a power. Okay, so the number of let me rewrite it. The cardinality of omega, which is the outcome set of the experiment, is going to be the cardinality of the trial outcome to the power of the number of trials. There we go. So that would be an easy one to come up with the cardinality. But then there's not much we can do about the distribution of probability. So the only thing we can easily come up with is the cardinality of the experiment outcome set. Okay, when the trial outcome does not equal to 2. So when the cardinality of trial outcomes is exactly 2, then we can still do this, right? This still applies in the case of this one. But on top of that, we can also use binomial distribution. So let me just kind of emphasize that whatever you can do for this case also applies here. It's just that we have that one extra thing that we can do, which is using binomial distribution. All right, so is that okay? I mean, does everybody understand what this hierarchy of questions is about and how to use it? Well, go ahead and give this a try. Okay, so use this to try to solve the problem that I posed today, because you're gonna need it. Yeah, well, I mean, it's just a quick summary of the essence of each kind of counting slash probability problem. So there are some of these are just counting. Okay, so when we look at cardinality, that's counting, right? Because all we are doing is to count the number of outcomes of an entire experiment. And the same thing applies to whenever you apply permutation or whenever you apply combination, you're also dealing with just counting. Probability is when you have the cardinality of an event, which is typically computed by either this or using permutation or combination, divided by the cardinality of omega. Then you have probability. So if you remember, okay, prime example. Okay, this one we have been beating it for so long that it's definitely dead. Okay, lottery. Okay, so when we deal with lottery, the number of tickets that can win a specific prize, that's counting, right? But the chances of you getting something in return of buying your lotto ticket, that's probability. So how do you go from counting to probability? You divide the count by the total number of possible tickets. Then you have probability. So that's also important, because otherwise you just come up with a count of something and by itself is useless because it doesn't tell you about the probability of winning the jackpot. Okay, it just tells you that one ticket out of 200, close to 300 million tickets, only one of them is gonna win the jackpot. Okay, but if I only tell you that one ticket is going to win the jackpot, that is helpless. Okay, it doesn't help you to decide whether you should buy a lotto ticket or not, because you don't know your actual chances of winning the jackpot. Okay, so I hope that is making sense. So whenever you do counting and the question is asking about probability, that means you probably need to figure out what you're supposed to divide it by. All right. So all of this stuff here is supposed to help you with trying to answer that question in the questions channel. Please do not post your answer. You can post some questions if you want to, but please don't post your answer in the questions channel. And then on Wednesday, I'm going to show you how to do that calculation. Okay, so try to use these 2 days to kind of apply what you have learned to solve that problem. It's not going to be graded, simply because that's actually coming out of the final exam 1 year ago. And I think I might have posted the solution online on YouTube already. So, I mean, but it is a good exercise, okay? Because this is a mixture of a bunch of stuff, okay? So when you start to analyze the problem, you'll say, wait, hold on a second here. It looks a little bit like a counting problem, but it also looks a little bit like a binomial distribution kind of problem. Well, so I'll give you a clue that I did not give my students a year ago. It is both. Okay, so now you have to kind of think about how it can be both at the same time, and which part is which part. Okay, so that's kind of the thing that you can do. Okay, now the second thing you can also do, okay, I know you probably cannot get it done in 2 days, but you can think about it, is if you want to write a simulation program to simulate the problem in order to empirically determine the actual probability, how would you have written that program? Okay, because by going through that process, by writing the emulation program, okay, to simulate the activities involved in the question, that will also help you decide which part of the problem is a counting problem and which part of the problem is a binomial distribution problem. All right, so all of these are bits and pieces to try to kind of give you, in other words, I'm giving you a box of puzzle pieces, okay? And you'll just try to figure out how to put all the puzzle pieces together, because they connect in a certain way. So your job is to kind of study the shape of each puzzle piece and then figure out which piece connects to which piece for this particular problem. All right, so trial outcome caret number trials is strictly for permutations with replacement, not combination. Let's see. It is for permutation. Yes, that is correct. It is only for permutation where ordering is important. Yep. All right. So with that said, okay, we have now concluded the topic of discrete probability. The next topic down the line is graph. Okay, and this is where some people can go like, "Oh, I learned this already in CISP 430." Sorry. Um, when it is, well, sort of. You might have learned this in CISP 430. Some people are taking 430 this semester. So for those people, has Iraj talked about Dijkstra's algorithm yet at this point? If anyone is taking it from Iraj. Not yet. Okay, so that's okay. Not a problem. All right. So this is a special warning to people who are taking CISP 430 and CISP 440 at the same time. In CISP 430, they're probably using an algorithm that is very similar to what I describe as Dijkstra's algorithm here. But this particular Dijkstra's algorithm is modified. Okay, so I suppose in some literatures it would have been called Dijkstra-All-Young algorithm because it has a little spin of my modification to it. It's not anything significant, so I really don't think my name deserves to be a part of the name of the algorithm, but it's kind of cool. So by the time we get there, you guys would go like, oh, okay, so it is different from the one that you're going to use in CISP 430. So I just want to bring awareness to the differentiation between these two algorithms. When is our next exam? Well, what do you think? What is our next exam according to the syllabus? It's the final exam, yes. So the final exam is based on the final exam schedule. In other words, this is a fully synchronous class. The way we schedule the final exam for this class is exactly the same as an on-campus class, face-to-face on-campus class. So I think we might have talked about when the final exam is already. If not, when it's time, I'll remind you guys again. I mean, I'm going to teach you guys how to get there, right? So you just need to Google search for final exam schedule American River College. I'm literally just typing that in my browser, to do a Google search. And we get there. And it asks me these questions every single time. That part is a little bit annoying. So it's a daytime class. The lecture starts at noon. It's a Monday, Wednesday class. So we just need to look it up, right? Well, so it would seem to me that this matches our class, right? We start at noon, so that makes it between 12 p.m. and 1:10 p.m. It is a Monday, Wednesday class, so it meets the criterion of Monday, Wednesday, or Monday, Wednesday, Friday. So our exam date is on the Monday of May 16th. If somebody wants to take an exam on Sunday, I'm sorry, I cannot accommodate that. Okay, and the time is 12:45 to 2:45, so it's a 2-hour exam. So there you go. I'm pretty sure we have talked about this before, but it could just be me remembering something wrong. That's entirely possible too. All right. Oh, let me click that first. I want to read that one. Okay, corporate needs you to find the differences between this picture and this picture. Yes, in terms of topology, they are the same. All right. So let's go ahead and get into the graph concept. So for the most part, today we'll talk about the terms, and we might even get into a description of the algorithm, of Dijkstra's algorithm. But we'll probably not trace it. Okay, so I can give you, if you guys want to, I can give you a test case just so you can trace it a little bit and find out, what Dijkstra's algorithm would come up with as the solution. So I can do that, like after class. But before we do that, we're going to describe what a graph is. So a graph itself is a two-tuple. So this looks a little bit like when we talk about propositional logic, right? Or propositional calculus. So when we have a few sets, okay, that work together to represent something, we can use the tuple representation to basically say, yes, we have a set of vertices and then we have a set of edges. They are not completely independent to each other. There's a certain relationship that we have to establish between these two, but nonetheless, there are two sets, okay, in order to describe a graph. So this is one of those things that is consistent with how we describe propositional calculus. Is there are two components to a graph. The first component is a set of vertices. The second component is a set of edges. So right now is probably a good time to kind of describe, even though the final exam is not comprehensive in the sense of I will specifically ask you questions about set notations, set operations, and whatnot. It is implicitly comprehensive. In other words, when we look at Dijkstra's algorithm and also the A-star algorithm, it does make use of set operations and so on. So it is implicitly required that you still retain all of that stuff when you are attempting to answer questions related to graphs. Okay, so I just want to point that out, so that people do not let their guard down and go like, oh, I don't need to know set operations anymore. All of that intersection stuff and whatnot, I can throw it out the window. You may not want to do that right now. Okay, so you might want to retain all that stuff for the time being. There's little restriction of the set of vertices. So the set of vertices can be anything. Okay, so elements in that particular set. You can use numbers, you can use names, you can use letters, you can use subsets, right? You can use other set as members of this particular set. Okay, it doesn't matter. Okay, it just has to be a finite set for the most part. However, the nature of the set of edges depend on whether a graph is directed or not. So when we say a graph is directed, or a digraph, okay, di from the directed and then graph. So a digraph or a directed graph is when just knowing that you can go from one vertex to another vertex doesn't mean you can go backwards. Okay, so think about San Francisco downtown. That would be a good way to remind yourself what a digraph is. Okay, some of the streets are one way only. That would be a digraph. But there are also graphs where it is both, it's bidirectional, and we are not going to use bidirectional graphs in this class, so you don't have to worry about it. Is that okay? Does everybody kind of understand what a digraph is? It simply means the connectivity between the vertices is directional. You can Okay, let me proceed to talk about what an edge is first, and then it'll be clear what makes a digraph directed. All right, so this is a restriction. Okay, so this is a good reminder of why set notation is still useful, because what is this saying? We are using two specific set operators here. So we'll start with what looks like an X here. What is that notation? What does it mean? Cartesian product. Very good. Okay, good job. Okay, so this is not cardinality, it is Cartesian product. Okay. All right. So Cartesian product turns out to be a very, very useful concept, because we use that concept to describe functions, right? We use that concept to describe relations, and now we're using that concept to also describe, we also use that concept to describe permutations, but now we're using that concept to also describe what the set of edges is. Okay, so it has to be a subset of the Cartesian product between the set of vertices and itself. Okay, So you go like, okay, so it just has to be a subset, right? It can be equal to, it can be an empty set, because both of those are subset of, the Cartesian product of the set of vertices. All right, so this means that each edge is a two tuple. Now the two tuple, the two part of the two tuple simply means, oh, okay, highlighted the wrong part. So this 2 here is basically saying each tuple has 2 items. That's why it's called a 2 tuple. The first item and the second item are both elements of V. Recall that ordering is significant in a tuple. An edge on the digraph is usually drawn as an arrow going from the tail, which is the first item, to the head, which is the second item. A graph may be undirected. Such a graph can be seen as a special case of a digraph where, oh, this notation is coming back again, right? This if and only if thing, the element of, and this notation of tuple is coming back to haunt us, okay? So I should have said, for every vertices AB in V, this has to be true. What does that remind you of? So if you just kind of imagine that I also have a universal quantifier ahead of this that says for all AB in V, this has to be true. What does that remind you of? Symmetry. Very good. All right. Okay, I got to give you guys this. Excellent. Excellent. Okay. Excellent retention of what you have learned so far. So if we have symmetry within the set of edges, then we have what basically can be described as a bidirectional graph, or you can say undirected graph, okay, which means if you can go from A to B, you can also go from B to A. Okay, so this is sort of coincidental because we typically do not analyze or we do not have specific algorithms for undirected graphs, because every algorithm that works on a directed graph can also work on an undirected graph if we just make sure that the set of edges is symmetric. So that's kind of cool to kind of connect the two concepts, right? We are now introducing a new concept about graphs, but yet at the same time, we are relating it to relations, which is a concept that we have learned from before. All right, so getting back to the meme that that Danny posted earlier, I'm going to give you the text representation of that specific graph. So if you want to, you can go ahead and refer to that specific meme. So and then I'll give you the actual graph here. So G is VE, okay? So because we have a set of vertices and a set of edges, so in this case, the set of vertices, since they are just numbers, we have 1, 2, 3, 4. There we go. So that's pretty simple, right? The set of vertices is just labeled as 1, 2, 3, and 4 in this case. The set of edges, on the other hand, is also a set. But every time you see an arrow, then we basically use the tail of the arrow as the first item of a two tuple. And then the head of the arrow becomes the second item of the two tuple. So this has to do with how an arrow is constructed, right? Because the tail is the end that doesn't hurt, the head is the end that hurts or kills. So so we have 1, 4 as an edge in that specific graph. We have 2, 3 also as an edge. We have 1, 3 as an edge. Let's see, 1, 2, 3. There's one more from 3 to 4. There we go. All right, so this is the text representation of the graph that is in the meme that Danny posted a little bit earlier. Are there any questions about this very specific graph? All right. Now, I some of you know that I really like to split hair. So in hair splitting mode, okay, I'm going to say in the meme, they are not the same picture, okay? In other words, it is the same graph, but it is two representations of the same graph. There's a major difference between, are they just different things representing the same thing, or are they actually different things? I will give you an example of that one little hair-splitting sentence or statement. Okay, so here we go. I know you guys are saying, "Oh no, the hack tag is going off tangent again," but I think it's really important. Okay, these are very important things. Hair splitting is I would say, a necessity to become a computer science person. Okay, programmer, okay, tester, software engineer, and so on and so forth. We all need that hair splitting mentality. All right, so I'm going to give you this example, and I'll shut up about this. So this, and let's say I have to do some computation here. So these two are the same. Okay, they are different representations of the same value, because on one side we have 3, 4 as a hexadecimal number, so it's basically 3 times 16 plus 4. And on the other side, we have the much more familiar representation of the same value, which is 52. So if you want to include, human only human only representation, we can also say this is just 52, right? So all of these are representations of the same value. But so it depends on what you're asking. If you're asking, are they the same representation? The answer is no. But if you ask, are they representing the same thing? Then the answer is yes. Okay, so I shall get out of my hair splitting mode now. Yeah, just different names of the same thing. Okay, so if you're asking, are they the same? Well, are you talking about the name, or are you talking about what the name is referring to? Yes, in my mind, I'm already going there. I'm already going to aliasing in pointers in C++ or C++ programming. But I will refrain from going any further, in this digression. All right, cool. So now we talk about terms, and this used to be a lot longer. I just made it short enough that it only covers things that matters to us. Okay. So a path in a graph is a tuple of vertices. Okay, so let's just let's pause right here. It's a tuple of vertices. Okay, and there are some additional requirements, but let's just talk about what is a tuple, right? So a tuple is like an array. So when we talk about a tuple of vertices, it means every element in the tuple has to be from the set of V, which is the set of all vertices. Edges from E must lead from one vertex to the next in, well, okay, I didn't quite write that, but edges from E must lead from one vertex to the next in the tuple of vertices in the case of a path. So in other words, blah 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 blah. Okay, so you guys are looking at this and go like, no, not that kind of notation again. Well, that's kind of the whole purpose of introducing this kind of notation to begin with, okay? Because we want to be able to read this type of mathematical notation and understand what it means, okay? Because it usually sometimes it just translates to code, okay? All right, so let's kind of break this apart and find out what that means. Okay, what are we talking about here? All right, so the outermost part is a quantifier, a universal quantifier that says for all I as a natural number. Okay, so that means I can be 0, can be 1, can be 600, can be 902, and so on and so forth. But then we have some requirements. Okay, so this part here is an implication, which basically says if I is less than or equal to bar p bar, which is the length or the size of your tuple p, minus 2, if it is not less than or equal to 2, don't worry about it, because in an implication, if the left-hand side is false, the implication is going to be true anyway, right? So we are only paying attention to the right-hand side if and only if I is actually less than or equal to the size or the cardinal, I shouldn't say cardinality, but the number of elements in the path minus 2. Okay, so what makes it special, right? So what makes this condition special is this means I is an index into the path for the first except for the last element in the tuple, okay? Because bar p bar minus 1 is the index of the last one. Remember, a tuple is like an array, right? So the index of the last element in an array would be the number of elements in the array minus 1. But this is minus 2 because we only want I to be up to the second last element in the tuple. Alright, so knowing that I is an index from the first all the way up to the second to the last element of the tuple, what do we want? Well, these parentheses is forming a 2 tuple, and the first item in the 2 tuple is p bracket I. So p bracket I is basically saying we're using I to designate which item in the tuple do we want to refer to. The second item in this 2 tuple is p bracket I plus 1. So we are basically looking at 2 consecutive elements in the path, and we make a tuple out of those 2 vertices. And then we have the element of, right? This is, this little funny, funky looking E is element of, and this E is the set of edges. So this is basically saying every vertex in a path should be connected to the next one in the path with an edge. That's basically what this notation is trying to say. Are we good with that? All right, excellent. And then furthermore, a path cannot contain duplicates of a vertex. So that means when you look at all the elements within a path, you cannot have duplicate elements. Even though it's a tuple, by nature a tuple can have duplicate elements, but since we're using the term of a path, you cannot have the same vertex appearing more than once within a path. So you cannot have a loop, basically. All right. So the path can only traverse a vertex up to once. Yes. It can be 0 times, right? But you can only do it for up to once. All right. So I know we are about to run out of time, so I'm going to refer back to the meme picture. Okay. I have to thank Danny for presenting that meme because it's really helpful in our discussion. So a big thank to Danny. All right, cool. All right, so in this case, we can kind of look at a path. So P, as a path. Let's see, this is a really, really simple one. So a path can be just 1, 2, okay? And you look at this and go like, oh, no, it cannot be because there's no edge between 1 and 2. I misread, bad eyesight, the 3, I looked at it as 2. So 1, 3 is both an edge, but also a path, okay? And we can also look at the path as this. It's an empty path, and the only longer path in this case, because we only got, well, there are 2 longer paths. One is 1, 3, 4. That's a longer path. And then the other one, which has the same length, is 2, 3, 4. So those 2 are also paths. All right, so 1, 3 kind of makes sense, right? Because 1 is the second to the last item in the path, and then 1, 3 is definitely an edge itself, so it meets all the requirements to be a path. We'll skip to 1, 3, 4 first. Okay, so when we look at 1, 3, 4, then we look at the first 2 items first. Okay, is there an edge connecting 1, 2, 3? Yeah, the answer is yes, because we can actually see up here. And then the second question is, do we have an edge connecting 3 to 4? And then the answer is yes, we have that as well. So now it meets all the requirements of being a path. Same thing for 2, 3, 4. Okay, we are only replacing the first 2 with the 2 and the 3. It is an edge, and then 3 to 4 is common between these 2 paths, so no problem. So now we look at this empty set here, or empty tuple. I misspoke. This is an empty tuple. So the question is, why is an empty tuple also qualifying as a path? Now this is not the first time we see something like this. Okay, we have seen something like this when we talked about relations. Remember? An empty relation is also symmetric, right? An empty relation is automatically asymmetric. An empty relation is also automatically transitive. But how can it be all of those things when there are nothing in the relation? So one would not be a valid path because there's nothing for it to connect to. So one would not be a path. One as the only thing in the tuple would not be a path. Actually, okay, hold on a second. Nathan is onto something. So one is a path as well, okay, because it does meet this requirement here. So let's think about that case, okay? Let's think about those two special cases. I know we are running a little bit over time, but it is important to finish this discussion because we have all the context in our mind already, so it's important that we finish it now. All right, so the quantifier is basically saying I is just any natural number, right? So it can be totally insane relative to the example that we're looking at. So I can be like 6,000, right? So what if I is 6,000? 6,000 is less than or equal to, let's just say P is empty in this case. So if P is empty, then the length or the number of items in P would be 0. 0 minus 2 is negative 2. Is 6,000 less than or equal to 2? No, I don't think so. But since this is an implication, when the left-hand side is false, then the implication is true. So when I equals to 6,000, we don't have a problem of making this implication true. Not a problem, right? So now the question is, can you choose a natural number I such that this implication is false when P is an empty tuple? That's the question. So in other words, I'm trying to make the left-hand side true and then the right-hand side false. Can you make that happen? Can you find a natural number that is less than or equal to negative 2? The answer is no, right? Okay, very good. So since it's not possible to make the left-hand side of an implication true, that means you cannot make the implication itself false. Okay? All right. So that kind of shows the case when if P is an empty path, there's nothing in the path at all, then by its very nature, it has to be a path. Okay, it qualifies as a path. If a tuple is empty, it is a path in any graph. Okay. Second question: what if there's only one item? Like 1 is in P. Okay, so P is a one tuple with only 1 as the only member within the tuple itself. Well, same approach, okay? Same approach. Because in that case, the number of items in P is going to be 1. 1 minus 2 is negative 1. So in order to make the left-hand side of the implication true, you need to find a natural number that is less than or equal to negative 1. The answer is, I don't think there's one, right? Because natural numbers only start with 0. So by the very same argument, we also know that any path with only one single vertex, excuse me, I take it back. Any tuple with only one vertex in it is automatically qualifying as a path. Now, is it a meaningful path? Probably not, okay? Because when we want to study paths, most of the time we want to find a way to go from one vertex to some other vertices, okay? That's usually why we need to figure out a path. But if you want to ask, does a that's okay. Oh, okay, never mind. Okay, it's still okay. So if you want to ask, okay, if we know that an element within a tuple is a vertex already, but it's the only vertex in the tuple, is that tuple a path? The answer is yes. It is still a path. It's just not a very useful one, but nonetheless, it qualifies as a path based on these requirements here. There's one extra. Oh, okay. So there's this extra requirement that is not mathematically expressed. Is you first have to make sure that. Oh, okay. So it does qualify. Sorry, I kept going back and forth because I thought I wrote something else, but I wrote this. So a path needs to be a tuple of vertices. So if you have something other than a vertex within the tuple, it cannot be a path automatically. So this part is not expressed as a mathematical expression. I can do that too. I mean, I can easily express that as a part of the um, condition. I basically just have to say every element in P is in V. That's basically what I need to express here. But so there we go. Okay, so we are done with today's lecture, by describing the terms. But if you want to prepare for the lecture on Wednesday, okay, first thing is to work on the question that I posted in the questions channel. The second thing you might want to do is really just to look at the Dijkstra's algorithm. Okay, I will trace it on Wednesday so that we have a concrete example of what happens when we execute Dijkstra's algorithm, and we're going to use a spreadsheet to do it. But it will be very helpful if you just kind of get an overall idea of what is Dijkstra's algorithm. And if you want to, if you have time, and it's going to be super beneficial, is really just to give yourself, an example, to apply Dijkstra's algorithm to. The only thing the meme, did not include, as an example, is we don't have designation of what the destination vertices are. So if you want to, you can basically make 4 as the destination vertex. Okay, that's one way to do it. And it also does not have a distance function. In other words, the cost of going over one edge, each edge is not assigned in the graph of the meme. So you can just go ahead and assign any number as long as that number associated with an edge is non-negative, it will still work. Okay, so the only thing we have to avoid are negative distances between edges. Between vertices, or on edges. So as long as you can assign non-negative numbers to an edge as is d, you can go ahead and try to apply this algorithm yourself, and then on Wednesday we'll go over that in class. All right, so let me see if there are any questions. Nope. Okay, so let's go ahead and end today's lecture, and then we'll pick this up on Wednesday. Alrighty, I'll see you guys on Wednesday.